So in this video, we are going to be learning about dynamic programming, and this video is going to be part of a series of videos in which we'll try to cover dynamic programming in depth on this channel. So let's start. So what is dynamic programming? If I can say, I would just say it's a smart way of doing recursion. Okay, it's a smart way of doing recursion. How? We'll see. But the good part is that if you know recursion, you know half of the dynamic programming. Okay. How can we identify if a problem can be solved by recursion or not? So the main thing to notice while solving problem by recursion is you have to notice that if a problem can be broken down into subproblems. So if a problem can be broken down into different subproblems, and then the main problem could be solved by combining the solutions from these subproblems. Okay, so to understand this, let's take an example of a Fibonacci sequence. Okay, so a Fibonacci sequence can be generated through this formula. Okay, fn equals fn minus 1 plus f of n minus 2. Okay, so this formula is recursive in nature, right? Because f is calculated by calling f on smaller values, right? So this is one example of like you can write the code, recursive code, to solve this problem. Okay, so that is the first prerequisite to identify any problem as a dynamic programming problem. What else can we do? Okay, so what I said, that dynamic programming is a smart way to solve the problems recursively, right? What is smart about dynamic programming? So if you try to understand that, let's see. So let's say we want to calculate the Fibonacci of let's say 7. Okay, so we would call the function on 7. Okay, and it's a recursive call, so my first call would be f of 6. To get the answer for f of 7, we should know the answer of f of 6 and f of 5. Okay, and again, to get the answer f of 6, we should know f of 5 and similarly. So this is the call graph. Okay, and as you can see, there are a lot of calls. Like if we simply write the recursive function to solve this problem, there are a lot of calls, okay, just to calculate the value of f of 7. But also try to notice here that a lot of calls are being repeated. Let's talk about f of 3. So f of 3 is here. Okay, let's mark it with blue to make it clear. F of 3 is here, then 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 f of 3 is here. So as you can see, there are a lot of the function is getting called with same argument multiple times, right? So that is the cue that the question can be solved through dynamic programming. Okay, and dynamic programming is a smart way, smart recursion. What is smart about dynamic programming recursion? So thing is, we are not, if we write a normal function, normal recursive code to solve this, like what would be our code? We would simply say f of n and say int, let's say, if we have to calculate it, we would say f of return, right? But so this would be our recursive call, but also we would have to put some base condition, right? So always remember that recursive functions would always have a base condition. So what would be our base condition? It would be like if n less than equal to 1, then simply return n. Okay, so if n is 0, it's going to be, we are going to return 0. If n is 1, we are going to return 1. Okay, and we are assuming that function won't be called for the negative values. Okay, and for the normal case, we will just say f n minus 1 plus f of n minus 2. Okay, but if I try to convert it into, like, if I try to add some smartness into this program, I know that this function is being called with, if I have to calculate n, this function is being called with same value multiple times, right? As we saw here in this example, right? To calculate f of 7, we saw that how many, there are like multiple times where we are calling the function with the argument 3. Okay, so but what we can do is we would say that, okay, once I calculated the value of with argument value of 3, I'm just going to store it, and the next time if I get a call with the same value that I have already previously calculated, I'm going to just return it. So what I mean is, we can have some kind of storage, okay, and we would say that, so just to, like, I want to just modify this function now. So let's see something like this, okay, and if, let's say I have a table, okay, table, if tab of n is there, okay, let me write the pseudocode. Present, then return tab of n, simply. Otherwise what I would do is I would say, okay, also we have to store the value, right? So tab of n is going to be f of n minus 1 plus f of n minus 2, okay, and then I'm going to return the value n, right? Now what this function would do is, how it would be different is, whenever there is a function call here, we are not calling further down, right? So if you see this figure, let's say here for f of 3 we just called f of 2 and f of 1, and we like fetched the values and stored it in the tab. Now next time there is a call for f of 2, what would happen is, we won't make these calls, which is important. So we are avoiding a lot of calls, like we calculate once and we'll reuse. This is called top-down approach with memoization. Just some term, so you don't need to worry about that. Okay, recursion is top-down. Why? Because you see this calling graph, we are calling from top to bottom, right? Like to solve a bigger problem, we are going down to solve the smaller problems. Okay, so this is why this is called as top-down. Recursion is also called as top-down, and here I just added, in this approach is called top-down plus memoization. Okay, another optimization that we can do here after this is, like, we can convert this recursive program into an iterative solution. Why? Because maintaining, like, recursive programs take a lot of stack space, and maintaining and calling recursive program is an overhead to the operating system as compared to an iterative problem. Okay, so the next optimization we will try to do is we'll convert this program into an iterative solution. Okay, and the name that is given to that is called a bottom-up approach. Okay, so bottom-up approach for dynamic programming problems. Okay, so as the name suggests, let's look at this function called tree, okay, or graph. As the name suggests, bottom up, right? So what we would do is, like, we would start from the bottom and then we would build solutions for the bigger problems. Okay, remember that previously in the top-down approach, what we did is we started from the bigger value, like the top problem that we had to solve, and we broke down into the smaller sub problems. Okay, so the call basically went from f of 7 to f of 6, then f of 5, like this, like going towards the bottom. Okay, here we would start from the smaller value and we would build solution for the larger ones. Now how can I do that? So it's pretty easy if you see. So let's say I am taking this array, okay, and I know that f of 0 is 0 and f of 1 is 1. Okay, 0 and 1 are the first two Fibonacci numbers, and I would say that, okay, each index represents the nth Fibonacci number here. Okay. Okay, so now what would be the value of 2? Let's call this array ARR. So what would be the value of ARR 2? If it's a Fibonacci number, it would be the sum of ARR of 0 and ARR of 1. All right, and so what we would do is we would just sum this up. Okay. So now you see we know the value of 0, we knew the value of f of 0, and we knew the value of f of 1. So what we would do is we can combine the value of f of 2. Now to calculate f of 3, what do we know? F of 2 and f of 1, right? So that way we would build our solution to the top. So that's why it is called as the top bottoms up solution. Okay, let's see the code for all of this. Okay, so this is accepted, but you see it beats 42% of the solution. Okay, now let's try to optimize. Okay, so let's try to write the top down with memoization solution. Okay, so it's fine. It's already beating 100%. Okay, just by one simple improvement. All right. Now let's try to convert this into a bottom-up solution. You can do that yourself. Okay. You know what to do, right? We would just take an array and we would start from like you can follow that pseudocode. All right. So in the next video, we would build upon these concepts and we would solve a more classic dynamic programming problem, which would give you more in-depth analysis of how to identify a dynamic programming problem. So keep watching.